Greg Bothun is professor of physics at the University of Oregon, and he is coming to talk about cosmological models, tenacious beliefs, and epicycles. Over to you.
Okay. So let me first off define what I mean by an epicycle. First requirement is you need a wizard. Okay? And the wizard shows up and does an incantation, which produces a physically mysterious device which is completely misunderstood, but which is absolutely necessary to make the model work. In the literary world, this is called a Deus ex machina mechanism. The damsel's in distress. There's no logical recourse to rescue the damsel. A three-headed monster with 17 arms suddenly appears out of nowhere, saves the damsel in distress so the story can continue. Epicycles are similar as these literary plot devices. Scholars have traced that mechanism back to Euripides, who first used it about 100 years before Aristotle showed up. So maybe there was something in the early Greeks that gave them license to just make this stuff up. So once upon a time, cosmology was very simple. You could draw it on a piece of paper. This is the Aristotelian business card. It incorporates the Greek framework of earth, air, fire, and water. You stick in 55 crystalline spheres, because 55 is a nice number. The earth was the center of the universe. That was obvious from apparent sky motions. The earth will be ordained or proclaimed to be motionless, as we'll see in a moment. And physics was simple. In the earth realm, stuff fell straight down. Cannonballs went like that until they run out of destiny, and then they fell straight down. And if you weren't in the earthly realm, you orbited the center of the universe, i.e. one Aristotle place, in perfect circles because you were in the celestial realm. And then one day some prime mover, another epicycle, shows up and just kicks his sphere in one direction, so everything should be moving in one direction. And then we have Ptolemy defining our cultural truth, our cultural logical truth, by saying, well, it is manifest to any observer that the earth occupies the middle place in the cosmos and that all weights move toward it, thereby establishing the immobility of the earth. Well, now we have our first motion anomaly. Motion anomaly is going to figure prominently in cosmological models. Dark matter is a motion anomaly. Dark energy essentially is also a motion anomaly, as we'll get to. And so we're not obeying the prime mover here. Mars is moving backwards in an obvious way. Every 90 days out of every 2 years, any observer could plot the position of Mars with respect to the constellation and say, hey, it's moving backwards. It's not supposed to. Prime mover said it's got to be moving in this direction. So when confronted with an anomaly, you have three choices of what you can do. The simplest choice is to pretend it doesn't exist or it's bad data. There are two other choices that are available, however. You could actually use the anomaly to inform a new model. That's an advanced scientific concept, seldom used. But you could do this. And Aristarchus did this in 220 BC or so. Here's a figure that he drew in the sand to explain retrograde motion as a natural consequence of a heliocentric solar system. But he's up against the cultural truth that the Earth can't move. So let's not do this. Instead, let's make an even more complicated diagram in the sand, because that means we're clever. And of course, this gets it right because it explains retrograde motion and keeps us locked to an immobile Earth. So this must be the right cosmology, and indeed it lasts for 1,800 years. That's pretty damn good for cosmological models. All right, now because nobody could accurately measure the positions of planets, the Ptolemaic epicycles work operationally great for making a calendar. Right? If you want to know where Mars is going to be in the spring 10 years from now, well, fine, it'll work. But there was a lot of speculation and writing about a moving Earth by many philosophers and scientists, and I'll just discuss a few here. Nicholas Erasmus was the first one to do a thought experiment. He was a bishop in Paris. And all he said was, look, if I'm up in the heavens looking down on the earth, I'm going to see it rotating around underneath me. So if I'm on the earth looking up, I'm going to see everything rotating around me. Big deal. That was sort of the first thought experiment that the earth could at least be moving on its own axis. Of course, cows are not observed to be flying away from the earth, because the concept, this is what I tell my students, if you've been told about linear velocity of the earth in 25,000 miles an hour and you're worried about it, I just want you to go home, invite your friends, and rotate once in your residence every 24 hours, and ask your friends if you're moving fast. So the concept of angular velocity is not really understood, but Oresme is posing that. More importantly, Cardinal Nicholas Cusa, who's a strong pre-runner to what Copernicus would say, didn't have a printing press, just wrote by hand an Italian obscure piece of paper and left them in monasteries. But his work is really quite important. We talk about Kepler and Copernicus and Newton in historical astronomy classes. This guy should not be left out. Learned Ignorance is his main document, and it covers lots of facets of modern day relativity, lots of cosmology, but it's a treatise on the concept of relative motion before anything else. And under that context of relative motion, he raises the issue many times about the motion of the Earth. The Earth, which cannot be the center of the universe, must in some way be in motion. This idea of heliocentrism also figures prominently in many Islamic cosmological models in the year 800 to 1000. So long before Copernicus, there are ideas and writings and sketches about heliocentric cosmology. There's just no printing press, the internet at the time, to publish it. So Copernicus has a printing press. And I found some old referee reports about Copernicus' paper on the moving Earth. Now also, contrary to what we tell our students, Copernicus' contemporaries weren't really upset that he removed the Earth from the center of the universe and replaced it with the sun. That wasn't really the problem. The problem was the moving Earth. That's the problem. So here's one referee, the first referee, that says, but that is how things go nowadays. Anyone who wants to be clever must not let himself like what others do. He must produce his own product, as this man does, who wishes to turn the whole of astronomy upside down. I'm sure you've all got referee reports about turning a discipline upside down. This one's even better, and I've taken a lot of this language and have used it in recent letters for tenure and referee reports. It's great, because nobody writes like this anymore. This actually comes from a textbook that was published right after Copernicus' work was published. Out of love for novelty, or in order to make a show of their cleverness, some people have argued that the Earth moves. Even though subtle experts institute many investigations for the sake of exercising their ingenuity, nevertheless, public proclamations of absurd opinions is indecent and sets a harmful example. Let us cherish the truth, for after all, we writers of the textbook know the truth. And let us not permit ourselves to be alienated from the truth by the tricks of those who deem it an intellectual honor to introduce confusion into the arts. And then Galileo comes along and he messes everything up because he makes a scientific instrument. Discovers all kinds of stuff. Spends 15 nights in January looking at Jupiter and notices, hey, there's 4 little things orbiting a big thing. Wow, what a model. And he discovers that, empirically, that there's obviously more than one center of revolution or rotation in the universe. And he's observing a mini solar system because he built an instrument that could detect it. And then we have Newton's problem, which has been alluded to before, in that, oh, gee, gravity, I don't really know how it works, but I can express it formulaically. But what it means is all the mass is trying to gravitate with all the other mass. So why am I here to write this? Why has the universe collapsed? And so this is from Newton's own words, where he uses the concept that, well, the only way I'm going to get out of this is I have to make the universe infinite. Because in an infinite universe, there'll be no direction for gravity to have a net fall, so the universe will remain there as a static deal, being infinite. And he emphasizes that. He says, to make an infinite number of great masses scattered at great distances from one another throughout all that infinite space. So, the universe is infinite. That's Newton's epicycle. It's infinite. It wasn't infinite. For Aristotle, you could draw it on a piece of paper. Once you got to sphere number 55, that was it. No place to go. But now it's infinite. And then Herschel built this gigantic instrument at the time, and I think Caltech actually tried to hire him based on this. It didn't work out. And yes, he detected Uranus in 1789, but mostly he showed that, geez, there's a lot of stuff in the universe. There's a lot more stars than Galileo saw. There's a lot more stars than anybody's ever seen, because no one's looked through a 50-inch telescope before. There are a couple of, undergraduates he hires to move this thing around. And he made a map of the galaxy, which put the sun at the center. So, hooray for that. We get to be at the center of something again. We got removed for a while, now we got put back, so that's good. But that, of course, is just an illusion imposed by interstellar dust. The galaxy is optically thick in most places. If I filled up this room with a fog, which I may be doing intellectually, but if I did with a physical fog, then all of you would think you're in the center of the distribution because you couldn't see anything. Now we get to another orbital anomaly. Okay, Uranus is discovered in 1789. 50 years later, people are noticing through precise measurements of the orbit of Uranus that it's not moving the way that Newton told planets they need to move. Something's going on. So now, for the first time, we can ask this scientific question raised by Ken Freeman, so you can add this. Is this dark matter? Is there some piece of unseen matter out there that's perturbing the orbit of Uranus? Well, yes, there is. At the time, there was some piece of unseen matter. And as more and more data converged on the precise orbit of Uranus, on September 23rd, 1846, people were told, point a telescope over there, let us know what you see, let us know if you see any dark matter, and voila, Neptune is discovered, not dark matter, just baryonic mass. Okay. Well, 13 years later, we have another problem. 1859, every 88 days, Mercury gives us a new ellipse. Well, Newton said Mercury shouldn't do that. Anything orbiting in flat space in equilibrium, this orbits in flat space in equilibrium, and you're done. Simple problem. So you apply the same, wow, is there an unseen object? And that was quickly ruled out. There is no unseen object explanation for the precession of the orbit of Mercury. Now we're stuck, now we're screwed, because now you have a lab experiment that you've just done, and first and only one done, that shows that Newton is actually wrong. Newtonian theory doesn't work. Well, let's scratch our heads for 45 years, and then try and figure out what works. Fortunately, Einstein came along and randomly scribbled some characters on a rusty train. The train's actually not big enough for him to add the third term, so it's not there yet. But we don't need it for this. And we resolve the orbit of Mercury by declaring that space-time looks like that. And Newton didn't think of that. Didn't understand curvature. Curvature's an advanced concept. It's a whacked concept, right? I mean, it's very difficult. I don't understand it. I don't know what space-time curvature is and how that maps into gravity from a point of physical intuition. I understand how to use it. I understand we think that's the right answer. I don't really understand it. And then we have Einstein's epicycle that we heard a little bit in the previous talk from. I'll present it in a different way. It looks like that. That's terrible. Get rid of that and replace it just with the answer. P equals minus rho c squared. Rho is a mass density. For you historians, there is no such thing as negative mass. So that's an absurd equation. We can't have negative mass. We can't have a negative mass density. So that's okay. I'll just change the equation. That's fine, I can live with that. I now no longer have any negative mass to worry about. Yeah, I got this minus p thing to worry about. Yeah, that's all right. I can deal with negative pressure. Okay? But that's because that's a lot better than negative mass density. Well, this has two very strong implications. One, the first one is the universe is precisely balanced. If Descartes' evil genius comes around and kicks the universe just for the hell of it, because that's the evil genius hypothesis, let me screw with the world and see if anybody notices, then it's unbalanced. It's either going to collapse irretrievably or it's going to expand irretrievably. So Einstein places the universe at a point of unstable equilibrium. That's a very unsatisfactory solution. You live in the period of cosmology when the universe is in unstable equilibrium. Not likely. But this introduction of minus p has given us three cosmological characters which we can now use to transition to our modern cosmology. And that's what they look like. We have three energy densities out there. We got us, little baryons, mostly hydrogen. We don't matter. Good about that. We've got this guy who's going to have a big personality conflict and complex in a little while. And then we have this large character out here, omega sub lambda. One of the reasons we have that is that supernovas say I am real, question mark, which we'll get to. And as we'll see, this middle character is now greatly confused on what it is and how much of it there is, because there's a lot less of it now than there used to be. And we'll get to that part of the story now. The next big problem, the next epicycle, so to speak, that's required is that of inflation in order to fix really a fundamental physics problem. Is that the universe that's over there in that 1 square degree of sky, and the universe that's over there that's in that 1 square degree of sky have never exchanged information. Yet both universes are exactly the same. And there's 45,000 of those universes in the sky. So how can they all be exactly the same if they never had any causal contact? That would be magic. We don't believe in wizards or magic. So inflation solves a problem in a very simple way. It just says, okay, this room is the initial conditions of the next universe. Fine, it's heterogeneous, it's different over there than over there. But this little point right here, well, that's homogeneous in that little point. I'm going to incant some magic vacuum energy instability, let it inflate exponentially, so I live in a homogeneous universe. I don't care where you guys live, it doesn't matter, I live in my universe. So, and that's a profound resolution to this problem, but it makes some very important scientific truths that data must fit. I'll tell you that story now. It requires the universe to be flat. All the curvature got inflated out. Again, something I tell my students, simple experiment, go find a basketball, stand on top of it, have your friend inflate the radius of curvature of the basketball by 10 to the 50, and ask yourself whether you see curvature. It's all inflated out. So the large-scale energy density is 1 in cosmological units. Well, that would be great if all the gas and dust and baryonic material that we had an inventory of in the universe was also equal to 1, because what you see is in what you get, and we're done. But in fact, it's not even close to that. At the time, in 1980, when galaxy detection was still difficult and the like, our catalogs of matter in the universe, when you added them all up, you only got 0.5%, 0.5% of the material that's required to set this known energy scale of 1. Well, that's a problem. And therefore, since we already know the answer, omega equals 1, because inflation must be the resolution of the horizon problem, then we now require a dark matter dominated universe. Now, this isn't just a bunch of words here. This is affected very strongly funding. Off-particle physics went on many dark matter searches because we absolutely know it's there, because inflation tells us it must be there. So money that could have been spent for astronomical instrumentation and larger telescopes at the time, in fact, went to particle dark matter searches. This is the way the world works, right? You are pre-constrained by some idea that must be the truth, and then you build instruments to find that truth. I'll come back to that momentarily. So by 1985, this is the known truth. Inflation satisfactorily describes our cosmology. We require dark matter, whatever the hell it is, to be 99.5% of the energy density of the universe. This lambda term is 0. We don't need it. Simple cosmology. If we only knew what the dark matter was. Now, I talked about lines in the sand being drawn by earlier people. Well, in the mid-'80s, a bunch of people that I used to associate with drew this line in the sand, drew this model, and came up with that as an answer for how much gravitational energy density is. 0.2, not 1. Remember that. Because now we have another episode of faith versus science. Observations don't matter. You've already heard that. Observations don't matter. We know omega is 1. The universe is dark matter dominated. We know all of this. End of story. We're done. That little drawing you guys drew in the stand, you observers, that's irrelevant. You didn't get the right answer. You got 0.2, not 1. Now we have the new Aristotelian pod, our new cultural and scientific truth. Now, whenever you claim the old truth is gone, the new truth is here, you have to critically examine what aspects of the old truth went away. Well, where the hell did the dark matter go? It used to be 99.5%, now it's 20%. Gee, 20%. Gee, that sounds really familiar, that 20% number. Where have I seen that before? It's whatever dynamical experiment was done, infall to the vertical cluster, peculiar velocity fields, all that stuff, returned untemplated answers of 0.2. Okay, if you wanted to smooth everything on large scales, theorists made 0.2 into 1. Now that's another story. But in fact, this truth that drives investment in particle physics experiments doesn't turn out to be quite so correct, according to our revised truth, where dark matter is suddenly shrunk by a factor of 5. In addition, and this is another talk, but I'll just raise a question, well, how come there are 8 times more baryons than there were in 1980? Where'd they come from? Well, we got a little more clever at looking for elusive baryons, but you don't quite get to the 4% number. And of course, Aristotle's completely unhappy with us because we've taken his certain model, added 2 epicycles to it, dark matter and dark energy, and have a complete lack of any physical understanding of anything about the large-scale nature of the universe. That's not the way science should evolve. You're supposed to know more, not less. Now, there's some observational support for this idea of vacuum energy, which I'll discuss briefly because it did result in a Nobel Prize awarded last year. This is just a representation of a supernova that would occur in some galaxy, and as you go back in distance, the galaxy gets smaller and smaller and smaller. So if we simply assume that there's no evolution explosion physics of the thing that's producing the light, even though we don't understand the physical mechanism detail of these explosions, and we assume that all host galaxy environments are the same, even though galaxies evolve, somebody once told me that. Under those assumptions, we can recover evidence for vacuum energy. And at the very largest distances we now probe, you can't see the underlying galaxy anymore, over the supernova. Which begs kind of a lab rat question. Well, if you can't see the galaxy, detect the galaxy, how do you actually, but you know it's there, how do you actually subtract the light out from the galaxy to get a good estimate of what the intrinsic supernova magnitude is? That's another talk. So if we look at the 1998 diagram that produced the 2011 Nobel Prize, I just want to point out 2 things. The green line is the truth of the mid-'80s dark matter-dominated universe. The blue line is a de Sitter universe, no matter in it, just vacuum energy. The black line is the universe is open with omega matter equal 0.2, what the observers said. The important thing about the supernova data when they were published in 1998 is it completely does rule out the green model. Completely. We do not live in a dark matter-dominated universe. Data, green model. But it does not adequately distinguish either then or now between an open universe model and a lambda-dominated universe model, no matter how you want to, massage the data to make it appear so. So the real result, which I think was an important result, it's not the immediate result. The immediate result is the universe is accelerating, look out. But the important scientific result is we completely rule out the mid-1980s cosmology through supernova. And that's worth a Nobel Prize, so that's fine. Now, there could be statistics involved. Don't care about that, too much astronomy. Other than this little puzzle. So, the supernova are assumed to be, I take two white dwarfs, I merge them together, and the combined mass of the merger puts me above the Chandrasekhar limit, my system's unstable, and it goes boom. Well, that's a nice idea if it only worked out with respect to the available seeds for merger. So if you look at the white dwarf mass function of our galaxy, and this is the only galaxy you can measure it in, you find, well, A, there aren't many white dwarfs with mass greater than 0.7 solar mass to begin with. Most of them are 0.55 solar masses. And if you just do a Monte Carlo and then say, I'm going to randomly sample this distribution. I'm going to pull out a white dwarf, I'm going to pull out a white dwarf, I'm going to stick them together and ask, did you blow up? The answer is generally no, and you get a supernova rate of 1 every 10,000 years in our galaxy, if that's the mechanism. So there are problems here with our understanding of supernova and the mechanisms. Just 2 more slides to go, I promise. And now we're left with the nature of dark energy, right? Well, we got 4 ideas, each one of them astonishingly horrible in its own right, and challenge our physical understanding. We have Einstein's original idea of, let me just fill the universe up with negative P. I don't know where it comes from, I don't care. Future physicists will invent a term called vacuum energy and say some stuff about it, which I'm not going to understand. But that's the original idea. W is the equation of state parameter, is what the hope is for precision measurements of supernova, between a redshift of about 0.7 and about 1.5. That precision has to be 5%. We have to know supernova intrinsic luminosity of 5%, which I don't think is possible. That's just me, in order to possibly probe what W is. We want to know if it's greater than -1, consistent with -1, or less than -1. If it's less than -1, then Plato was right. We have quintessence out there. We have some weird decaying particle field. If it's not equal to -1, if it's less than -1, we get all the headlines. The big rip. There'll be a time in the future when the distance between 2 protons in a carbon nucleus is such that the expansive velocity is the speed of light. Okay, fine. I'll be dead by then. I don't really care. But there's a lot of interest in that from theoretical physics. And there's this idea that we don't understand gravity, which I'm going to come back to. So let me just summarize this. The main message here ought to be obvious. In a historical context, no cosmology should ever be viewed as correct or free from epicycles. We've never had one. Why do we suddenly have one now? In terms of the dark matter epicycle, there's no detection yet. There's some iffy stuff in some caves in Italy, but the signal noise is pretty low in terms of WIMP detections, but we really haven't found it yet. How many more years of negative dark matter searches are there going to be before somebody says, maybe there isn't any? Probably more than 30 years, hopefully not less than 300. Now, dark energy, everybody has their favorite explanation. And a personal hobby of mine is to try and maximally confuse my students with a minimum amount of words, believe it or not. And so my explanation when students say, hey, what's dark energy? I simply say this. Empty space creates exponentially more empty space. And here's a nod to Lucretius, who got basically everything right 2,000 years ago. This is why he's laughing his ass off right now. He's going, yeah, that makes sense. Nothingness creates more nothingness at an increasing rate of nothingness creation. This is what I said in my poem 2,000 years ago on the nature of things. But that's operationally what's going on. The rate of surface area in the universe is exponentially increasing with time because empty space exists, because the vacuum exists. If any of you can figure this out, you'll get the next Nobel Prize. This is a very, very complex thing. And it may be something that is symptomatic of an even deeper situation. Just like GR is or Newtonian space-time is a subset of general relativity, It turns out, and this is an entirely separate talk, that you can resolve both the apparent nature of the lambda term and the dark matter term by saying something which nobody believes. Well, this has happened. People do this. And that is, maybe the universe is more complex than we think. Maybe in certain environments there's a difference between the gravitational mass of an object and its inertial mass of an object. That will actually explain, in a qualitative way, both dark energy and dark matter. But it requires Einstein's principle of equivalence to be broken. And this is merely a restatement that maybe we need more than 10,000 years as a species of thinking about the complexity of space-time before we've actually understood it. Thanks for your time.
I think we've more or less basically run ourselves out of time for questions, but I must make sure that one statement you made there is challenged.
Good.
And that is where you said that there were heliocentric considerations in the Islamic
All right.
period. There's absolutely no evidence known for that.
Well, there's not much. I run across a couple of things, but I agree that that's a legitimate bone of contention here.
Okay. There are other things. Harry, do you want to ask the one question? Oh, there's another.
It was difficult to follow your arguments because when you came to modern time, you didn't quote names and you didn't quote arguments behind them. So your idea of epicycles, like hiding in every theory, modern theory, is you didn't defend it, in fact, because from where who gave this number 5.5% of a matter?
Oh, that's all over the astrophysical literature in the early 80s.
Who? Maybe it's popular people who wrote popular books. Who?
No, you just take a look at the galaxy catalogs, the Zwicky catalog, the RC3 at the time, on the basic space density of galaxies, you know, and what their mass is, and you come up with a number. It may not be 0.5%, but in the range of 0.5% to 1%.
You have to quote names. And,
Now, nearly everybody in that row wants to ask a question.
I just can't resist three quick points. First of all, first of all, in dark energy, okay? First of all, there are multiple lines of evidence. You pick one. There's a much bigger story. That's the trouble with. I know it's hard to do it, but you pick one.
Louder, please.
I would say.
I think total omega is the best argument given inflation. Omega equals 1, you get the lambda by subtraction. That's a very valid argument. I agree with that.
No, you can measure the. Let me start from the beginning. You can make measurements of the geometry of the universe from the perturbations in the cosmic background radiation. But that's what my major point is. There are several lines of evidence, not just one. First point. Second point is, when you say no cosmology should be viewed as correct, I don't know any physicist who says that. I hate that sort of straw man argument. There isn't the first physicist in the world who would say correct. What they do say is they think it's better than the last one.
I'm not talking about physicists. I'm talking about culture when I make that statement.
Okay, fair enough. And then the third point is, in terms of culture, I think it is a misunderstanding, and I do see this all the time because I deal with the public. It's not that we say this model is correct, blah, 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 therefore there has to be that much dark matter. That's the wrong way around. The argument is, if the model is correct, then that would imply there's that much dark matter. That's a completely different thing, you know. And I hope to say more about that this afternoon. But it's an if-then clause. We're not saying it's right, but we are saying if it is right, well then we can make a definite prediction, and that's the power of science. And I feel that this.
Oh, I agree. I just don't think we use the word if.
I'll give you a chance to talk about that more this afternoon. Maybe you can hammer that out in the breaks. But did you have a?
I'll make a quick point. Only that, well, you know this, but you didn't have time to say on the very last question that there's the observation of how much visible matter you see, and there you get various versions of very, very low numbers, even lower than what you
There's a cosmic
But
web.
when you do Big Bang nucleosynthesis,
Right.
you get somewhat higher value. But those calculations don't give you omega baryons directly, they give you omega baryon times the Hubble constant normalized squared, which would be called Stephen constant. But back in the day, we all thought, or who all quoted the numbers use 100 for the
Right.
Hubble constant
Right.
instead of 70, and that gives you a factor of 2 right
Yep.
there, and so on. So when you add all those pieces together, it's not quite the discrepancy.
Well, I would just, my astrophysical response is, we don't know the baryon density by factor of 2 today. That I would say, I still agree with that.
Yeah.